How is it going?
Enjoy the show.
What if every mathematical proof you've ever encountered actually came with an energy bill?
An energy bill, you mean like
Echo?
electricity?
Yeah, exactly. Not just the brain power, but a literal thermodynamic cost.
That's a wild thought.
Imagine just for a second that every logical step, every axiom you use consumes a measurable amount of energy, like computational energy.
Okay, elegant proofs would be cheaper.
Right. And the really tangled, convoluted ones would rack up a huge bill.
I see where you're going with this. It changes how you think about a proof.
Exactly. Today on the deep dive, we're plunging into mathematics with a pulse, proofs, primes, and spectral logic.
Spectral logic.
Our mission today is to unpack this groundbreaking framework. It dares to turn abstract mathematical reasoning into something physical, measurable.
Moving math from just abstract symbols to something with physical property.
We're going to explore how proofs can be seen as these thermodynamic journeys, right? Where every step has a quantifiable cost.
And the primes. You mentioned primes.
And how prime numbers, those fundamental atoms of arithmetic, act like the building blocks, the very atoms of reasoning itself in this model.
Okay, primes as atoms of reasoning.
So get ready, because this deep dive might fundamentally shift how you think about mathematical truth.
Yeah.
And its beauty.
It's definitely a radical departure from traditional math, where a proof is just valid or invalid. That's it.
It's binary.
This new approach, spectral logic, introduces a fascinating geometry to proofs. It assigns a quantifiable cost, or energy, to every single step inside them.
Wow, okay, geometry of proofs, that's a remarkable shift. If a proof isn't just a string of correct statements, but like a path with an energy signature, how do you even start assigning a cost to logic?
That's the million-dollar question, and it's precisely the core innovation here. The idea is that proofs aren't just true, they have this inherent elegance or economy, and you can measure it quantitatively.
How do you measure elegance?
The way it works is by assigning unique numerical weights to the axioms.
Axioms, okay, the basic starting points, the self-evident truths.
Each axiom, let's call it AI, gets a weight that's derived from the F prime number.
Wait, from prime numbers like 2, 3, 5, 7.
Specifically, the weight is Ys, where pi is the ith prime, and is called the spectral parameter.
Pi to the minus s. What does these do?
It adjusts how sensitive our measurement is to the different primes. Higher primes usually mean more complex axioms.
Ah, so a smaller prime, like 2 for basic arithmetic, that would contribute less to the cost. Foundational stuff is cheaper.
You got it. The first prime, 2, gives a weight of 2s. The next 3 gives 3s, and so on. Foundational axioms linked to smaller primes generally have lower cost.
The total energy, the spectral cost of a proof, is just summing up all these weights for the axioms used.
Exactly. You sum the prime-weighted costs for all axioms used, and you count how many times each one is used. Multiplicity matters.
Right, but what about the logic itself? The if A, then B steps?
Crucial point. Those structural rules, logical inference steps.
Really?
They're like the free energy of the system. You don't pay for the connections, just for the foundational ideas you bring in.
Okay, so this isn't just mathematicians arguing about which proof is prettier anymore. Now there's an actual number, an energy cost.
It's like mathematicians finally get their utility bills.
Exactly. And if a proof has a lower spectral cost, it really is more elegant in this framework. It makes me think of that line from the research, something like, beauty isn't hand-wavy, it's a lower spectral cost.
It gives a concrete definition to something usually considered subjective. And what's really fascinating here, I think, is that the primes, they aren't arbitrary choices for these weights.
So why primes?
Think about primes. They're the fundamental atoms of arithmetic, right? Invisible building blocks.
Yeah, it can be broken down further.
They're algorithmically random, incompressible. That makes them perfect examples of these inviolable, system-defining rules.
So they act like fixed points, anchors for the system.
Almost like the fundamental constants or constraints that govern how we even get knowledge in the first place.
That helps make it more tangible. But let's get even more concrete. You said we can compare costs. Can we apply this to a famous proof?
Absolutely. Let's try one everyone knows.
How about Euclid's proof? There are infinitely many primes. It's ancient, elegant, classic.
Perfect example. Let's imagine a really simplified system for Euclid.
Okay.
We could say basic arithmetic axioms, stuff like associative, distributivity.
The most basic. Cost 2 is 2.
Then maybe division algorithms they map to prime.
Okay.
And the crucial idea that every number greater than 1 has a prime divisor. Let's map that to prime 5. Cost equals 5s.
So every time Euclid uses one of those ideas, We add its prime-weighted cost to the proof's running total, like a meter ticking.
Euclid's proof works by constructing a number.
The product of all known primes plus 1, P1 times P2 times Pk plus 1.
And then he shows its prime factors can't be among P1 to Pk, so there must be new primes.
Where do the costs come in?
Well, when Euclid says, let P1 Pk be a finite list, that involves basic definitions.
Makes sense.
Constructing the number n Pk plus 1, that's more basic arithmetic. Another hit of twos.
Okay.
When he considers if n is prime or composite, and if composite, it must have a prime divisor.
Ah, that's your prime 5 axiom, the existence of prime divisor.
Exactly. Add fives to the bill. We'll just count. How many times did he use A1, prime 2, A2, prime 3, maybe the division part, A3, prime 5? Sum those pi's costs, counting the multiplicities.
And you get a final number, a finite quantifiable cost for Euclid's proof.
A true energy bill for a 2,300-year-old thought process.
That's incredible. And it lets us compare proofs. What about other proofs of infinite primes, like Euler's proof using analysis?
Great question. Euler's proofs uses different tools, right? Properties of infinite series, the zeta function itself, actually.
Yeah, much heavier machinery, you might say.
Potentially heavier axioms mapped to larger primes. But maybe Euler uses fewer axioms overall, or uses them more cleverly.
So even with heavier axioms, his proof could be more economical, more elegant in this spectral sense for certain values.
It depends on the specific mapping and the value of is. It highlights that efficiency isn't just about using cheap parts, but how efficiently you assemble them.
Does that mean sometimes the most fundamental truths, if you use them a lot, could actually be the most expensive to access?
That's a really perceptive point. Yes, absolutely. A proof might use a few very heavy, complex axioms, high primes, but use them very directly.
And its cost could be lower.
Lower than a proof that just keeps hammering away with lots and lots of cheaper axioms.
Yeah.
It's about the efficiency of the entire path, the whole journey.
A thermodynamic journey.
Exactly. And this thinking leads us naturally to another concept, the proof partition function. We call it Z-proof.
Z-proof. Okay, partition function. That sounds like thermodynamics or statistical mechanics.
Think of Z-proof as mapping out a vast statistical landscape.
Yeah.
Every possible proof for a given theorem is like a little path on this landscape, each with its own energy. Z-proof basically sums up all these possible paths, but it weighs them by their energy. Low-energy proofs contribute more. It's like a meta-zeta function.
A meta-zeta organizing the universe of proofs for one theorem.
In a sense, yes. It quantifies the entire possibility space, and if we add another parameter, beta, which acts like inverse temperature in physics.
Turning the heat up or down?
Exactly. High beta, low temperature, makes axiom costs really matter. Low beta, high temperature, they matter less. This can reveal different phases of mathematical reasoning.
Phases, like ice, water, steam, but for proofs.
Different regimes where different kinds of proof structures might dominate. It's a way to study the collective behavior of proofs.
That's a really powerful lens, a thermodynamic landscape of truth. If we can measure the cost of building mathematical structure, what about the opposite? What about measuring the cost of anti-structure, chaos?
Fantastic question. And yes, spectral logic has been used to look at exactly that. We can compare the spectral costs for proving things about highly structured objects versus inherently chaotic ones.
Give me an example.
Think about arithmetic progression sets, AP sets. Sequences like 2, 4, 6, 8. Very regular high structure.
Got it, like neat rows of bricks.
Right. Now compare those to Seiden sets.
Seiden sets, I vaguely remember those. They're weird, right?
Right. They're specifically designed for collision-free chaos. Every sum of two distinct elements in a set has to be unique. They actively resist additive structure.
So AP sets are orderly, and sets are deliberately jumbled to avoid patterns in their sums, like a random pile where no two pairs add up the same?
That's a great way to put it. Now, what happens when we apply spectral logic? We look at the proofs about properties of these sets.
What do we find?
Using a standard spectral parameter, S2, the difference is pretty stark.
Oh, yeah.
The average spectral cost for proofs about AP sets, the structured ones, that's around 0.026.
0.026. And Seiden sets, the chaotic ones.
The average cost jumps to about 0.063.
Whoa. 0.026 versus 0.063. That's almost 2.5 times more expensive for the anti-structure?
Exactly. The ratio is roughly 2.4. It's significantly more expensive energetically to prove things about anti-structure.
What does that mean, though?
It suggests something profound. Creating or proving properties about disorder, about anti-structure, is energetically harder. It's like structure naturally rides downhill in terms of spectral costs.
While building chaos requires you to climb uphill.
That's the interpretation. It's not just a feeling, it's a quantitative measure. It seems mathematical systems, or at least our ways of reasoning about them, might inherently favor order. Or at least it takes more work to rigorously define chaos.
That's fascinating. An inherent bias towards structure may be baked into the math itself. Proofs have energy, order costs less than chaos. But you tease something even stranger. When the measuring stick measures itself.
This is where it gets really interesting. Almost self-aware. We need to talk about the Riemann zeta function.
Okay, Phyllis, the music of the primes, deeply connected to prime numbers. It's some mind-bending stuff.
It is. And in spectral logic, when we analyze proofs about the zeta function itself, it starts playing multiple roles at once.
Multiple roles, how so?
We find it playing 3 simultaneous self-referential roles.
3 roles? This sounds like Hofstadter's strange loops or something.
But it really has that flavor. Okay, role number 1. The zeta function is the content, the thing we're proving stuff about.
Like the Basel problem,
Right.
finding the value of things.
Exactly. Proving that dia2 equals 6, which is about 1.645. 6 is the content.
What's role 2?
The z function is the structure of our measurement tool itself.
How?
Remember the axiom weights based on primes?
Yeah.
Well, the zeta function is fundamentally defined by primes. The CDS is the sum of ones, but it's also a product over primes. Those terms pi's that define our weights. They are literally the building blocks, the factors in the Euler product form of the zeta function.
So the primes defining the function we're studying are the same primes defining the weights we're using to measure the proof about that function.
Precisely. The mathematical object under analysis is also defining the metric we're using to analyze it.
Whoa, what's 3?
It helps define that proof partition function, z-proof, that we talked about. That's sum over all possible proofs. The zeta function structure informs that calculation too, becomes part of the landscape definition.
Let me see if I get this. The zeta function is 1, the thing being studied, 2, the ruler being used to measure the proof via prime weights pi's, and 3, it shapes the entire space of all possible proofs.
The z-proof, you've got it. Content, metric, and landscape framework.
That level of self-reference is,
Yes.
yeah, mind-bending is the word. So what happens when you actually do the calculation for the Basel problem?
The revelation. When spectral logic calculates z-proof for proving v2, specifically at S2, we find z-proof S2 is approximately 3.729.
3.729, and D2 itself is about 1.645.
Correct. Now take the ratio R z-proof 2.
Okay, 3.729 divided by 1.645, that's roughly 2.27.
Yes, that's the ratio of self-awareness.
What does that number 2.27 actually tell us?
It tells us something profound. The content to the actual value 6 is this single elegant number, 1.645.
Right.
But the structure, the z-proof, representing the thermodynamic mass or richness of all possible ways to prove that result, is about 2.27 times larger.
The effort or complexity involved in proving it across all possible proofs is more than double the value itself.
It's like the underlying mathematical reasoning, the structural depth required, is churning away with about 2.3 times more complexity or multiplicity than the single result it outputs.
It's not just a static truth. The process of knowing, the structure holding it up, has significantly more weight?
Exactly. It carries more weight, more complexity than the final theorem alone suggests. It's like the universe isn't just about the final answers, but about the incredibly rich, energetic dance of how those laws are found, proven, and interconnected.
That challenges the idea of math truths as these isolated facts.
It really does. And this ratio R, the strength of the strange loop, it changes with S and beta. It suggests math has these internal dynamics, these thermodynamic properties. It's the first quantitative measure we've ever had of mathematical self-reflection.
It's like looking at an iceberg. The theorem is the tip, but z-proof is the massive hidden structure underneath, and this ratio tells us how much bigger it is.
That's a perfect analogy. Understanding this has real implications.
Where does this lead?
Think about automated proof search. AI trying to find new mathematical proof.
Okay.
This framework offers powerful new heuristics. Instead of just searching for any valid proof, an AI could be guided to search for low-cost, elegant proofs first.
You give the AI a sense of taste, a preference for elegance defined by spectral cost.
Exactly. It's a more human-like approach, prioritizing efficiency and beauty, not just brute force correctness.
That could be huge for AI theorem provers. What else?
It also gives us a principled way to measure and compare elegance in those big formal proof libraries, like in systems called Lean or Coq.
So you could analyze those libraries and see which proofs are the most economical, identify the foundational insights versus the messy detours.
We can start mapping the thermodynamic landscape of existing mathematical knowledge. See where the efficient highways are, where the costly mountains are?
This really does feel like turning metamathematics, the study of math itself, into an experimental science.
It's a crucial step in that direction. We can start asking questions like, what are the thermodynamic properties? It's metabolic rates.
What does that mean?
It means asking things like, how much energy does it take to connect two different fields of math? What's the temperature of a specific theory? How much freedom or constraint is there? What's the most efficient way for a new idea to spread through the network of mathematical knowledge?
So we move beyond just checking if something's true to understanding the cost and the flow of truth itself.
Exactly. The dynamics of knowledge. It's potentially a new era.
Okay, but I can hear the skeptics already. Is this just fancy numerology, finding patterns in primes? Could you just pick any weighting scheme?
Excellent questions. And important ones to address. First, no, it's not numerology. The primes aren't arbitrary. They're unique mathematical properties like the connection to the zeta function. They're fundamental.
And other weights don't work?
Researchers have tried. They've plugged in random weights or weights based on other sequences. The strong correlations, the meaningful structures like the Z-proof behavior tend to just collapse. It seems primes are special here. The choice is backed by empirical fits in the models and convergence tests.
Okay, so the primes seem necessary, but does this whole idea giving truth a cost? Does it somehow threaten the philosophical idea of mathematical truths existing independently? Platonism.
The answer is no, not really.
How so?
Think about Gödel's incompleteness theorems. They tell us about fundamental limits on what can be decided or proven within a formal system. Spectral logic doesn't change that.
It doesn't remove those limits.
It adds a new layer on top. It adds a resource geometry. It tells us about the cost or difficulty of accessing the truths that are decidable. It's like getting a topographical map of the mathematical landscape.
The map shows you the hills and valleys, the easy paths and the hard climbs, but it doesn't change where the peaks are or remove the cliffs.
Beautifully put. It has a cost function without changing the underlying truth values or the fundamental boundaries described by Gödel. It maps the terrain of provability.
Okay, that makes sense.
They're thinking more broadly that this idea of structure and cost connects to how knowledge works in general, even in our minds or in AI.
Oh, you mean?
The act of learning, weaving new facts into what you already know, fundamentally changes the structure of your understanding. It creates persistent features. We call them topological scars.
Topological scars, that's a striking phrase.
Think of them as deep structural relationships, like twists or knots in the fabric of your knowledge that are really hard to undo. They're not just surface details.
Trying to truly unlearn something deeply ingrained feels impossible sometimes because it's left a mark, a scar.
Exactly. That's why forgetting things in complex systems, like large AI models, is so difficult. You can try to patch over the scar, approximate unlearning, but the underlying structure often remains detectable.
True erasure needs...
What? It needs what you might call topological surgery, basically rebuilding significant parts of the system. This connects back to physics. Landauer's principle says information erasure has a fundamental energy cost.
Knowledge has inertia. It costs energy to acquire and energy to erase because it leaves these structural scars.
That seems to be the picture emerging. The data linking spectral logic directly to cognitive science is still small, but the parallels are compelling.
This deep dive into spectral logic started with math proofs and energy bills, went through primes and chaos, looped through the zeta function, and now it's touching on how we even know things.
It really spans from the foundations of math to the structure of knowledge itself.
We've seen primes give axioms weight, proofs get energy costs, and the Riemann zeta function revealing that the hidden structural mass of reasoning can be more than double the result itself.
Indeed. Mathematics isn't just describing the universe. Maybe it's the first system where we can actually measure the process of knowing itself.
Think about the knowledge you gain every day. Does it have a cost? Is there an elegance metric to your understanding? Could learning that new skill, that new fact, be creating topological scars in your cognitive space?
It's a fascinating lens to turn on ourselves.
Spectral logic isn't just a new way to look at math. It's potentially a profound way to think about how knowledge itself is built, weighed, stored, and maybe even erased. The abyss of proofs isn't just deep, it turns out, it's spectral.
A landscape with energy costs.
We encourage you to explore these ideas further. Picture them like strings on an instrument, each one ready to hum its own unique tune.
The latest deep dives into mathematical theory are beginning to suggest a far more fluid, resonant universe of numbers. This raises an important question. What if our traditional view is fundamentally incomplete? What if we've been looking at a still image when the reality is a vibrant, moving picture?
Exactly.
That's the key.
Through the lens of waves, vibrations, and even quantum mechanics.
And as we journey through these concepts, you'll discover how numbers don't just exist.
They sing. Our understanding of numbers has been largely based on them being symbols of absolute certainty, rigid points on a continuum. We've seen them as the immutable bedrock of logic, the unyielding skeleton of reality itself.
This perspective posits that the very laws of number theory, especially the profound symmetries we observe in modular arithmetic, are the natural consequence of the resonant frequencies produced by these arithmetic strings.
So the laws emerge from the vibrations.
That's the idea. What's truly fascinating is that this framework suggests that a law as elegant and foundational as quadratic reciprocity, which links the properties of two seemingly unrelated numbers, suggests that law is a direct result of universal laws of sympathetic resonance in the numerical domain. It's like discovering that the harmony in music is encoded within the very structure of the instrument itself.
If we're running with this string idea, we're asked to forget the familiar image of a number as just a dot on a number line.
Leave the number line behind for a moment.
Our sources ask us to imagine every integer as a unique one-dimensional object. It's arithmetic string. But if we're truly imagining these as strings, how do we define them? What are their fundamental properties beyond just saying it's a string? How do we begin to measure and understand this new kind of numerical existence?
To truly grasp what an arithmetic string is, we need to consider three key properties that give it its unique acoustic signature. The first is its length.
Okay, length, but probably not length like inches or centimeter.
Definitely not. Now, this isn't linear magnitude like a physical ruler would measure. Instead, it's a logarithmic measure of its multiplicative complexity.
Multiplicative complexity, what does that mean exactly?
Let's take the number 12 as an example. Traditionally, we see its length as simply 11 plus 1, or just its position.
Right.
But in arithmetic acoustics, its length is related to its fundamental structure as 2 squared times 3. It's prime factorization.
Ah, okay, so it's about the building blocks.
Precisely. Think of a prime number like 7 as a single fundamental note, a relatively short, simple string in this analogy. A composite number like 12, made of 2 and or 3, has a more complex internal structure, like a richer chord, or maybe a string composed of multiple intertwined fibers. This makes its arithmetic string conceptually longer and capable of more intricate sounds.
So it's the unique fingerprint of its prime factors that dictates its acoustic length.
Exactly. It's the architecture.
This profound reorientation. So the complexity of its prime factorization, not just its size, determines its length. It's about its architectural makeup rather than its position on the number line.
Precisely. And this leads us to the second property, tension.
Tension, like a guitar string needs tension to make a sound.
This tension is determined by the specific number system, or modulus, mod n, in which we place the string. Our sources explain this beautifully. Placing a number a into a system, mod n, is akin to attaching that arithmetic string to a frame of size n.
Okay, so the modulus acts like the tuning peg in the bridge.
This modular context effectively gives it a specific tension. Different moduli mean different tensions, and thus different potential vibrations and resonant behaviors. It's the environment, the mod n system, that defines how the number will resonate.
The context matters. And finally, the vibration itself. If it's not physical movement, what is this dynamic characteristic? How does an abstract number vibrate?
The vibration is defined as a multiplicative oscillation, a pattern that unfolds as the number multiplies itself and interacts with other numbers within that specific modular system.
Multiplicative oscillation. So how it behaves when you multiply it repeatedly.
Yes, exactly. It's the dynamic behavior of the number when its movement is constrained by the modulus. Think of it less as a physical shake and more as a recurring pattern, a rhythmic pulse in its multiplicative behavior. For instance, consider the powers of a number modulo n. Does the sequence AAA no mod n repeat quickly? Does it jump around the modular space in a predictable or seemingly chaotic way? That dynamic pattern, that unfolding behavior, is its unique vibration.
So it truly defines a dynamic rather than static existence for numbers. It's about their behavior within a system.
Precisely. It's relational.
Just like a guitar string has a fundamental note, the lowest, purest sound it can make, what's the simplest sound an arithmetic string makes, what's its purest tone, its most basic resonant frequency in this acoustic universe.
The simplest mode, or fundamental frequency, is what our sources call a binary vibration. +1 and
-1, that sounds simple.
deceptively simple, perhaps. This corresponds directly to the property of squareness within a modular system.
Squareness, like whether a number is a perfect square.
Exactly, but within that modular system. It's the most elementary, non-trivial multiplicative oscillation. When a number A is placed in a system, mod n, the fundamental question we ask is it a square in that system? Meaning, can A be expressed as x Satzenqual for some integer x within that modulus n?
And what does that mean for its vibration? Does it vibrate differently if it's a square versus if it's not?
Absolutely. That's the core of this fundamental frequency. If a Satz is a square modulo n, what mathematicians call a quadratic residue, its string vibrates in the +1 phase.
+1 for squares.
Think of this as a stable in-phase oscillation. If it is not a square, a quadratic non-residue, it vibrates in the modic 1 phase.
-1 for non-squares.
Right, an out-of-phase oscillation. So
Okay.
it's a fundamental binary on or off state, or maybe better, an in-phase or out-of-phase state. It's a rhythmic pulse between these two possibilities.
So we can actually see these vibrational sequences, these patterns of squareness. Our sources give specific examples. For modulus n7, the sequence of squareness for numbers 1 through 6 is +1, +1, -1, +1, -1, -1.
That's right. 1, 2, and 4 are squares mod 7. The others aren't.
And for n11, it's +1, -1, +1, +1, -1, -1, +1 for numbers 1 through 10. At first glance, they might seem a bit chaotic, but you're saying they're not random at all. They're perfectly ordered.
Precisely. That sequence, that pattern of +1s and -1s, is the fundamental harmonic of that specific modular system, its purest, most elementary sound signature. It is demonstrably not random, but a perfect, distortion-free
Wave. How is a sequence of plus and minus ones a wave?
In formal mathematical terms, this sequence is known as the quadratic character, often written using the symbol. It satisfies a crucial property. The character of a product is the product of the characters.
This multiplicativity property is the defining signature of a perfect distortion in this context. It means the phase, +1 or -1, behaves predictably under multiplication. It confirms its status as a pure tone in this multiplicative space, a fundamental rhythm that underpins the entire modular system. So this quadratic character is the most elementary beat or rhythmic pulse of a number system, its unique harmonic identity. It's a foundational concept in understanding how these arithmetic strings resonate. It's the simplest song a number system can sing, and all other more complex harmonics, all the richer chords, are built upon this fundamental binary pulse.
Indeed. It's the acoustic equivalent of the purest tuning fork for a given modulus. Once you understand this fundamental frequency, you're ready to explore how these individual number strings interact with each other, which is where things get really fascinating.
Think about a classic physics phenomenon, sympathetic resonance.
Right.
If you pluck a C string on one guitar and a nearby piano's C string softly begins to vibrate in response, that's sympathetic resonance. It's a non-local interaction, a hidden connection. How does this apply to numbers? If numbers are vibrating strings, how do they hear each other across the mathematical landscape?
This is a perfect analogy. And we connect this to the bigger picture. The profound law of quadratic reciprocity, LQR, is the arithmetic version of this very phenomenon.
Okay. LQR as sympathetic resonance.
Precisely. It describes exactly how the vibration of one arithmetic string, say string M, let's use primes P and Q to be specific, is heard and responded to by string Q and vice versa. It's the fundamental law of sympathetic resonance in the world of numbers, revealing their deep, interconnected vibrational nature.
So let's truly unpack this law of quadratic reciprocity. Our sources describe it brilliantly in terms of two distinct measurements, almost like observing how two separate musical instruments respond to each other.
Imagine we have two distinct arithmetic strings represented by prime numbers P and Q. We need two different primes, not two. The first measurement is like plucking string P near Q. We are measuring the vibrational state of P within the modular system, mod Q.
So we're asking how P sounds in the environment set by Q.
This is mathematically captured by the Legendre symbol, PQ, which gives us a +1 or -1 value, essentially, the fundamental cone of P as perceived by Q. It asks, is P a square when observed in the context of Q?
Measure, PQ.
Got it.
And then the inverse measurement, plucking string Q near P.
We measure the vibrational state of Q within the modular system, mod P. This is represented by QP. This gives us the fundamental tone of Q as perceived by P. And what's truly remarkable, what our sources call the shocking claim in the heart of reciprocity, is that these two measurements are not independent. They're deeply linked. The tone of P in system, mod Q, is usually identical to the tone of Q in system, mod P.
So tone of P near Q, tone of Q near P, most of the time. That implies a profound and startling symmetry, almost like a perfect reflection or echo across the numerical universe. What makes it so significant? Why isn't it always equal?
Well, the fact that it's almost always equal is already huge. This isn't just a coincidence. Our sources describe this profound connection as repackaging the reciprocity law as a diffraction pattern rule, or a phase locking rule.
Phase locking, like oscillators syncing up.
Exactly. It's not merely an abstract formula, it's a statement about an interference effect between these numerical vibrations. Think about the product of these two outcomes, PQ, QP. This product is almost always +1, precisely. This +1 signifies constructive interference, a perfectly harmonious symmetric interaction. It's a profound statement of inherent symmetry in the numerical universe, suggesting a cooperative, complementary relationship between these arithmetic strings. This implies a layered and incredibly complex sound that numbers can produce, extending far beyond the fundamental binary and into a full, intricate spectrum of numerical acoustics.
So the full set of these higher-order reciprocity laws, meticulously organized by modern mathematical theory, describes nothing less than the complete harmonic spectrum of integers.
That's the grand vision.
It's not just a collection of formulas, it's a music of breathtaking complexity and beauty. This truly sounds like a grand, universal symphony played out by the numbers themselves.
This is precisely where class field theory comes into play.
Okay, I've heard of that. It's notoriously difficult.
It is deep, yes. It's often described as the grand symphony of numbers, or more technically, a complete orchestration of modular structure. It is the pinnacle of algebraic number theory, providing the unifying framework that brings all these individual harmonic laws, these discrete vibrational patterns together into a single, cohesive, breathtaking whole. It explains how these overtones are generated and how they relate to one another systematically.
What are the key components of the symphony? What are the major movements or sections that give it its structure? Can we break it down a bit?
The Kronecker-Weber theorem serves as the harmonic base layer of this symphony. It's a foundational result. It demonstrates that all abelian extensions of the rational numbers, essentially all number fields that have a relatively simple commutative group structure controlling their symmetries, can be found within what are called cyclotomic fields.
Cyclotomic fields, generated by roots of unity, right, like the cube roots we mentioned for cubic reciprocity.
Exactly. Those roots of unity are crucial. This theorem provides the foundational harmony, the initial chord from which all other related melodies emerge. Building upon that, we have the
Hilbert class field.
This can be seen as representing the perfect overtones for a given number field. It represents the maximal unramified abelian extension. Unramified essentially means the harmony is pure, without introducing any noise or points where primes behave badly into the number system's structure.
So the purest higher harmonics.
Yes, it captures a very fundamental part of the field's arithmetic structure.
And what about the Langlands program? That sounds like the ultimate conductor attempting to unify everything. It comes up everywhere these days.
It really does. The Langlands program is described as the unifying theory of all global vibrations. It's often called a field resonance unification, or playfully, Langlands plus. It's an enormous, far-reaching set of conjectures that proposes incredibly deep and unexpected connections between seemingly disparate areas of mathematics.
Like what areas?
Imagine finding a secret Rosetta Stone that translates between two entirely different mathematical languages, say, the world of abstract number theory, specifically Galois representations, which we'll get to, and the world of continuous functions and harmonic analysis, automorphic forms.
That sounds impossible. Discrete versus continuous.
That's why it's so profound. Langlands aims to show that the vibrations of numbers, these Galois representations, are deeply mirrored by patterns in these continuous mathematical objects. It's an attempt to find the universal rules that govern all these numerical vibrations, unifying these diverse harmonic theories into a single cohesive framework. It's one of the biggest stories in modern math.
Lest this sound like mere poetry or a beautiful but abstract analogy, what is this arithmetic string in precise mathematical terms? What's its scientific definition beyond the beautiful image of a vibrating object? Where is the rigor? We need the math.
Absolutely. In modern mathematics, the vibrating string we've been discussing is formally defined as a Galois representation. The string itself is embodied by the absolute Galois group of the rational numbers, Gal.
Gal Q bar over Q. That object sounds formidable.
It's incredibly complex. It mathematically encodes every possible symmetry of every algebraic number, numbers that are roots of polynomial equations with rational coefficients. It's the ultimate structure, a kind of master key that governs all algebraic relationships and properties within the number system. Think of it as the blueprint of all number symmetries.
So the string is this incredibly intricate group of symmetries, but what about the actual vibrations or harmonics that we've been describing?
Great question. The vibrations or harmonics are mathematically realized as one-dimensional representations or characters of this Galois group. These characters essentially act as filters or lenses. They map the complex, multifaceted symmetries encoded in the full Galois group down to simpler numerical values like the +1 of the quadratic character or the roots of unity for higher harmonics.
So they simplify the view.
Exactly. They simplify how we observe these intricate symmetries, allowing us to hear a specific note or measure a specific property. The quadratic character, for example, the +101 vibration, is a unique elementary representation. It technically factors through a simpler Galois group related to square roots, Galois.
Ah, okay. And the law of quadratic reciprocity, the sympathetic resonance between numbers we discussed earlier, how does that fit into this rigorous framework of Galois groups and representations?
The law of reciprocity, in its various forms,
Yeah.
quadratic, cubic, etc., is then revealed as a deep, profound theorem within this structure. Specifically, it's encompassed by the Arden reciprocity law. This law precisely governs how these Galois representations behave when you look at them locally, meaning how they behave with respect to individual prime numbers, like in our PQ and QP measurements. It dictates the resonance.
So the arithmetic string is not a physical object in our universe,
No, definitely not physical.
but it is a very real, tangible, mathematical object. It is a structure of pure symmetry, and the laws of number theory, including all the reciprocity laws, are simply the fundamental rules governing its vibrations and resonant interactions.
Precisely. It's the intrinsic music of symmetry made manifest through the language of group representations.
That's truly fascinating. It means these sounds aren't just imagined. They're inherent properties of pure mathematical symmetry, captured by one of the most powerful tools in modern algebra. Let's shift gears slightly, but building on this. You know how light and matter in quantum physics can behave as both particles and waves?
Sure, a cornerstone of quantum mechanics.
Our sources propose the same profound duality exists in mathematics itself within numbers.
Whoa.
This seems utterly revolutionary, even more mind-bending than the vibrating strings.
It really is. This raises an important question, maybe the most fundamental one yet. How can integers, which we typically perceive as the epitome of discrete points, also possess wave-like properties?
Yeah, how does that work?
Our sources clarify this by meticulously breaking down both the particle and wave nature of numbers, showing they are two sides of the same coin. Let's start with what we're most familiar with, the particle nature.
Right, the familiar aspect. Numbers as discrete, localized, definite points. 7 is just 7.
The particle nature of number is its most familiar and intuitive aspect. It's the bedrock of counting, everyday arithmetic, and digital computation. Think of its key properties. Discreteness.
1, 2, 3, distinct steps.
The number 7 is fundamentally distinct from 6 and 8. There are no other integers between them. Like a particle, it occupies a specific, unambiguous location on the number line. Then there's identity. 7 is always 7. It has a definite, unchanging value that can be measured with absolute precision, irrespective of its context. Finally, operations like addition and subtraction are local steps. To get from 7 to 8, you perform a single local increment, +1. The system progresses linearly, point by point.
And this particle model is formalized by the Peano axioms, which build natural numbers as a sequence of discrete successors. It's incredibly powerful. It gives us computers, all of classical arithmetic. But our sources say it has a fundamental limitation.
It does. While extraordinarily powerful for everyday arithmetic and computation, this particle view alone struggles to explain phenomena like spooky action at a distance, such as the quadratic reciprocity law we just discussed.
Where properties of P and Q are linked even though they seem far apart.
Exactly. How does the particle 7 know whether 11 is a square modulo it, and vice versa in such a symmetric way? The particle view doesn't naturally accommodate that. To understand these non-local, holistic, and relational properties, our sources suggest we must radically shift our perspective and observe the number not purely as a particle, but as a wave.
So how do we make that shift? How do we see the wave nature of a number?
Correct. To truly perceive their wave nature, we start listening to them in their natural environment, the multiplicative group modulo n.
The integers that have multiplicative inverses, right? The ones you can divide by.
Exactly. Imagine this finite number system, this group, as a kind of quantum chamber or resonant cavity. Within this confined cyclical space, the wave-like properties of numbers become manifest, much like how sound waves become apparent in an enclosed space like a concert hall.
So the structure of the Modern system itself acts like the instrument or the room.
That's a great way to think about it. This is where their inherent dynamics and relationships, their potential for interference and resonance are revealed.
And what are the key properties that define a number as a wave in this context? How do we quantify this waveness?
3 key wave properties emerge. First, there's delocalization. Unlike a particle, which is a single point, a wave is a distributed pattern that fills the entire space.
Like a ripple on a pond.
So a number's waveness in mod n isn't a property of the number in isolation, but a dynamic relationship it holds with the entire system. Its state depends on the whole structure. Second, phase. Just like a physical wave has a phase, its position in its cycle, numbers possess a multiplicative phase within these modular systems. This phase determines how it aligns or misaligns with other numbers.
Like our +1 and Monix 1 earlier, those were phases.
Exactly, the simplest phases. And third, interference. Number waves interfere. When 2 or more number waves coexist in a modular system, their phases interact, adding constructively, reinforcing each other, or destructively, canceling each other out, precisely like physical waves.
Interference. That sounds like where quadratic reciprocity came in.
It's deeply connected. The reciprocity laws are fundamentally about these interference patterns.
And what's the mathematical instrument or formal concept that perfectly captures this idea of a number as a pure wave? What object embodies this?
That would be the Dirichlet character. We mentioned characters before in the context of Galois representations.
Right.
A Dirichlet character modulo n is the mathematical formalization of a pure tone or a perfect wave within that modular system, mod n. It satisfies that crucial property.
The multiplicativity again.
Yes. This equation is the defining signature of a wave in this context. It means the phase of a product of numbers is essentially the sum, in a multiplicative sense, of their individual phases. This is analogous to how multiplying complex numbers on the unit circle corresponds to adding their angles or phases. It's the most coherent, distortion-free oscillation a number can perform within that system.
And the fundamental frequency of this number wave, the simplest one.
That's the quadratic character we discussed in the first part, the Legendre symbol. It maps a number to +1, which you can think of as phase 0 or in phase if it's a square modulo n, and -1, which is phase or out of phase if it's not. It's the simplest standing wave that this mod n quantum chamber can support.
The ground state vibration almost?
You can think of it that way. It's the number's most fundamental multiplicative vibration. When you observe this binary pattern of +1s and mod and 1s, you're not just looking at a fixed property like is it even or odd. You're measuring the number's wave state, revealing its dynamic relational identity rather than just its fixed particle identity.
Okay, this is really starting to click. So, if numbers truly have this wave-particle duality, how do we observe it directly? Our sources compare quadratic reciprocity to a double-slit experiment.
Which is the classic demonstration of wave-particle duality in physics, right?
Exactly. Can you elaborate on that powerful analogy? How is LQR like putting numbers through 2 slits?
What's truly fascinating here is that the law of quadratic reciprocity itself, encapsulated in its elegant formula PQ, Q12, Q12, is essentially the result of a mathematical experiment probing the wave-like interaction between 2 prime numbers, P and Q. Just as a double-slit experiment reveals the wave nature of electrons by showing their interference patterns on a screen, this law reveals the inherent wave nature of numbers by quantifying their interference, their mutual influence.
And the outcomes of these measurements, P and QP, are somehow entangled, just like in quantum physics. They're not independent.
That's the core insight. The 2 measurements or observations, QP and PQ, are not independent results. The formula shows they are correlated. It describes a precise interference effect between the 2.
How does the formula show interference?
QP isn't random. It's determined by that factor. This factor acts as a phase shift operator. For most pairs of primes, P and Q, this factor is +1. This signifies constructive interference, or what we can think of as a symmetric entanglement. They resonate in perfect harmony, their phases align.
Like waves adding up.
Right. But for those specific primes where both P and Q are of the form 4K plus 3, this factor becomes 1. This indicates destructive interference or a precise phase flip, as if their waves are perfectly designed to cancel each other out or be anti-correlated.
The law itself dictates the type of interference based on the shape of the primes.
Precisely. This demonstrates that the wave nature of numbers is inherently relational, manifesting through their interaction. The wave function of p, how it behaves mod q, is influenced by q, how q behaves mod p, and vice versa, in a predictable, symmetric, phase-locked way.
That's incredible. And our sources call this cognitive add SCFT for integers. Add SCFT in physics is this mind-blowing duality where a theory of gravity in a higher dimensional space, anti-de Sitter space, is equivalent to a quantum field theory without gravity on the boundary of that space.
It's a profound holographic principle.
So numbers behaving this way is like having a similar holographic principle, a secret connection across numerical dimensions captured by cognitive processes or mathematical structures.
It's definitely suggesting a deep structural analogy, maybe even more than an analogy. It implies that the complexity of these number-theoretic relationships might be captured by simpler boundary phenomena or vice versa. It's a very active area of theoretical exploration.
And this duality, this wave nature, it doesn't end with the fundamental frequency of squareness, right? You mentioned higher harmonics before.
Correct. Just like an electron can exist in excited states, moving to higher energy levels with more complex orbital shape, a number has a full spectrum of higher energy wave patterns within these modular systems. These are the higher-order Duflet characters we mentioned earlier, the ones related to cubic, quartic, and even higher reciprocity laws. Each one corresponds to a more complex, higher frequency vibration or wave pattern.
So each higher reciprocity law is like revealing another excited state, another possible waveform for the number.
Each law unveils a new, more intricate wave-like pattern that numbers can exhibit when interacting with mathematical structures, like fields containing complex roots of unity.
Okay, so if we connect this to the bigger picture, the complete set of all possible wave-like states of rational numbers, from the simplest quadratic character to the most complex higher-order ones, that's all described by class field theory.
Exactly. We mentioned it earlier as a grand symphony. In this quantum duality context, this monumental achievement of 20th century mathematics can truly be seen as the standard model of number theory, the complete harmonic spectrum, or the complete set of allowed quantum states for the rational number system.
The standard model of numbers, I like that.
Each reciprocity law, quadratic, cubic, or higher, reveals a new layer of wave-like structure, a rich internal spectrum of potential vibrations for numbers. This framework shows how numbers possess a rich internal life of potentiality and vibration, a true spectrum of numerical colors or tones that can be observed when we view them through a wave lens instead of just as static points. Your perception, your measurement, whether simple arithmetic or calculating a character, depends entirely on the question you ask. It really shows numbers living in a state of superposition until observed mathematically.
That is truly profound. It fundamentally reframes what a number is. And it's not just abstract theory. The parallels to quantum systems are also striking, given the binary nature of the quadratic character. It sounds like numbers are a natural arena for quantum analogies.
Quantum bits, or particle spin in quantum mechanics, also exist in fundamental binary states.
The basic unit of quantum information.
Reciprocity laws, with their precise phase-locking rules and interference patterns described by that Navigo factor, bear a striking resemblance to quantum conservation laws or entanglement phenomena, where the states of two particles remain correlated no matter how far apart they are.
The spooky action at a distance in numbers mirrors quantum entanglement.
The analogy is very strong. It suggests that the arithmetic of numbers might offer a profound toy model, or perhaps even a foundational blueprint for understanding the entanglement, symmetries, and phase relationships we observe in quantum field theory itself. Some research even explores using number theory to build quantum algorithms.
Our sources delve deeper into the quantum analogies. They propose something truly audacious, an arithmetic uncertainty principle. This is a direct echo of Heisenberg's uncertainty principle from quantum physics. What does it look like in the world of numbers? How can there be uncertainty in math?
It is a bold and fascinating claim, proposing a fundamental limit on simultaneous knowledge of certain arithmetic properties. The proposed relationship is x sub arithmetic.
Break that down. What are x sub x app and arithmetic?
Here, x is defined as modular localization. It represents the precision with which you can determine a number's congruence class, essentially, how well you know where it is in a specific modular system. The EAP is prime structure entropy. This relates to the inherent uncertainty or complexity in describing a number's precise prime factorization, or how it relates to the distribution of prime numbers generally.
So knowing its building blocks versus knowing its position in a cycle.
Exactly. The arithmetic Planck constant is proposed to be related to the prime context, may be defined as 1 log p, where p is a relevant prime energy scale. This principle suggests a profound trade-off. The more precisely you try to localize a number within a modular system, Inks is small, the less resolution you inherently get about its underlying prime structure, dt becomes large, and vice versa.
So you can't know both perfectly at the same time. That is like quantum uncertainty.
It's a profound echo of quantum reality, suggesting fundamental limits to information within the structure of numbers themselves. It connects back to that cognitive CFT idea, a deep structural link.
They even touch on quantum entanglement in this arithmetic context, which sounds mind-boggling. How can numbers be entangled? We talked about the analogy with LQR, but do they make it more concrete?
They do. This concept is made more concrete by looking at known statistical biases in the distribution of prime numbers, for example, how primes tend to avoid certain congruence classes after a previous prime. These correlations hint at predictable measurement disturbance effects on correlated primes, analogous to measuring one entangled particle affecting the state of the other.
Wow.
Furthermore, the double-slit analogy for modular interference is revisited with astonishing results. They calculate specific interference patterns or fringe patterns, exhibiting a remarkable fringe visibility close to 0.99. A visibility near 1 implies near-perfect coherence, like almost perfectly interfering waves. This suggests an almost ideal wave-like behavior in these numerical interactions, much stronger than just a loose analogy. It's as if numbers, when observed in specific ways, are perfectly synchronized in their quantum states.
This isn't just described as an analogy, but a fully fledged research program using tools from harmonic analysis, spectral theory, quantum mechanics directly to probe number theory. This is about building a full-blown arithmetic quantum mechanics.
That's the ambition outlined in some of this work. It means we can explore the timbre of a number, not just its fundamental note, quadratic character, but its full harmonic content, considering all its higher characters, cubic, quartic, etc., and how they blend together to give the number its unique sound.
By the dissonance.
We can analyze the dissonance between numbers, which refers precisely to those instances of reciprocity failure, like when the LQR factor, BKVQ, becomes -1. What causes this predictable anti-resonance? And we can study the spectrum of integers as a whole, understanding the complete range of their vibrational modes and interrelationships, much like physicists study the spectrum of hydrogen.
It really offers a radical new lens.
It hints at a potential full-blown arithmetic quantum mechanics, where numbers are not just static symbols for counting, but dynamic entities, like instruments in a universal symphony, generating their own complex, beautiful, and deeply structured music.
The implications of this extend far beyond pure mathematics, reaching into education and even philosophy. It's not just about understanding numbers, it's about re-understanding how we perceive reality itself, isn't it?
Absolutely. For education, this proposes a truly transformative shift. Imagine moving beyond just teaching children rote calculation.
Yeah, the drills.
Instead, we could teach them to listen to numbers' harmonic properties, to explore resonant patterns, mod n, and multiplicative rhythms from an early age. Imagine a curriculum where understanding the sound of a prime number, how it behaves multiplicatively, is as fundamental as knowing its value. It could cultivate a deeper, more intuitive, maybe even more artistic understanding of numbers and their interactions.
And for physics, the parallels are astonishing. It challenges our assumptions about the fundamental nature of reality itself, pushing on that connection between math and the physical world.
Indeed, the profound parallels between abstract number theory, Galois theory, reciprocity, characters, and the physical world, quantum mechanics, duality, interference, symmetry, are far too strong to be mere coincidence. They suggest a deep underlying unity in the logical structure of reality that compels us to ask, is the universe at its core mathematical? Is physical reality just one manifestation of these fundamental numerical laws and symmetries? Or is mathematics at its core physical? Is our mathematical language simply an abstraction derived from observing the inherent properties of reality?
Or is it a two-way street?
Perhaps, as our sources suggest, they are simply two different languages describing the exact same underlying quantum grammar of existence. This deep dive invites you, our listener, to conceptually build new kinds of particle accelerators and telescopes, not of steel and glass, but of pure mathematical logic and abstraction, to probe the quantum foam of arithmetic and perhaps hear the universe's most fundamental music.
So what does this all mean? Where does this leave us? We started by asking you to imagine numbers as vibrating strings, a seemingly wild and poetic idea.
Seemed almost metaphorical at first.
Right. And we've taken a deep dive into how that radical idea, formalized through concepts like arithmetic acoustics and quantum duality, reveals a hidden acoustic world within mathematics. A world of resonance, interference, and profound symmetries. It's truly mind-bending to consider that the very numbers we use every day have such a rich, dynamic inner life.
If we connect this to the bigger picture, the synthesis of these ideas suggests that the integers aren't silent, static monoliths, but vibrant, dynamic systems. Each number resonates with a fundamental tone, its quadratic character, and a whole spectrum of overtones. They are interconnected by universal laws of interference, like quadratic reciprocity, that govern their interactions.
So the universe of numbers is not silent at all?
It is filled with a subtle, intricate, and astonishingly beautiful music, if only we learn how to perceive it through these new mathematical lenses.
Throughout this discussion, you've seen how the rhythm of squareness acts as a fundamental tone, how quadratic reciprocity functions as a profound law of phase locking or sympathetic resonance between numbers, how higher reciprocity laws reveal rich overtones adding complexity to their harmonic spectrum, and how numbers themselves exhibit a profound wave-particle duality, behaving sometimes like discrete points and other times like interfering waves, all ultimately governed by the universal symmetries captured by Galois theory. It's a complete reimagining of the numerical universe, from static points to a dynamic symphony.
And perhaps the most provocative thought to leave you with is this. The fact that the abstract world of number, governed by logic and symmetry, and the physical world of matter and energy, governed by quantum mechanics, seem to share this fundamental wave-particle duality and are governed by analogous principles of resonance, interference, and uncertainty. That is truly astonishing.
It makes you wonder, what other hidden harmonies, profound dualities, or unexpected connections are waiting to be heard in the universe, both the physical universe we inhabit and the abstract universe of mathematics, if we only learn how to listen with a new kind of perception, with new mathematical tools and conceptual frameworks? What other music is out there?